So here, you read this problem, and do you have any do you have any ideas how to start this?
Looking at the cosine, that's kind of leading me to believe that, because I know we had previously talked about cross products,
Right.
But there's that relationship between the dot product and the magnitudes and cosine of theta.
All right, so let's grab that formula. We can find that up here. I should be able to find it up here. There we go. All right, so let me just grab this. Actually, I think I can just grab that and go back to where we are. All right, so there we have that.
Perfect.
All right. Okay, so we certainly need that. Any other things we can use?
Well, as far as calculating magnitude, that of course is going to be dealing with, taking the square root, that Pythagorean theorem.
Okay.
Essentially expanded out. So, and as far as dot product, I imagine we can calculate that pretty effectively just by, going through translating each of those equations into a vector form.
Okay. All right, so that's where we are. We certainly need to find some vectors. That's the key here. If we can find these vectors, it looks like if we can find the right vectors u and v, we can find the cosine.
Mm-hmm.
So the question is, what are the vectors that we want?
So that's probably where I would be inclined at first just to take the wild guess for our first, 4, -2, 1, but
Okay.
then there's that constant -1.
Okay.
And so, and then for the second, of course, taking the same guess, -2, -1, -3, 0.
Yeah. Okay.
But at the same time, I'm worried about the vector including that constant.
All right. So the question is, what does this equation, what do these coefficients actually represent? And do these coefficients actually represent the angle of the direction? How are these coefficients related to the direction of the plane? So let's look at this. We have 4x minus 2y plus 1z. 1z equals minus 1. Okay. All right. Now, okay. So let's. This can actually be written in the following way: 4, -2, 1 dot xyz is equal to -1.
Oh, interesting.
So, what is the? All right. So let's consider first. I'll consider first a related equation: 4, -2, 1 dot xyz equal to 0. What's the geometrical interpretation of this?
Well, when I'm looking at the vector 4, -2, 1, and I think about what the dot product means,
Yes.
I would normally think dot product to deal with sort of the expansion of a vector.
Okay.
Like its magnitude or its direction. The fact that it equals 0 would imply that they're orthogonal?
Yes.
Okay.
Yes. The 0 means orthogonal. Or what's the? There's a more common word for orthogonal.
Sure. Right angle. Or,
Yeah. Okay. All right. So what's at right angles to what?
So, I imagine the two planes, if you think geometrically, maybe these two planes are sitting at right angle to one another?
Well, I'm just taking the equation for one plane now.
Oh, okay, yeah.
This is a single plane here, so I don't have two planes involved so far.
Okay.
Let me go ahead and draw this vector. Okay, so we got 1, 2, 3, 4 out here, and then -2, would be back here somewhere. X, Y, Z. Minus 2 would be back here. So if we projected this into the plane, maybe a point here, and then we have to go up 1. So 1 is here. So we go up 1. So here it is. So a vector in three-dimensional space would look something like this. And then we can draw the arrow also. So there's my vector. Of course, this is, I hope you can see what's going on here. It's not in the xy plane. It's kind of going up a little bit. So this is the vector 4, negative 2, 1. All right, so the question is, what about this x, y, z? What is that talking about?
So is that in a search for, a vector that is orthogonal? So kind of, thinking backwards?
Yeah. And this represents, in this case, you're saying that any vector that's orthogonal to this vector is a part of this plane.
Sure.
The only condition on x, y, z is that it's orthogonal to this vector. So if I was going to draw the plane, it would look something like, I don't know how to do this, but something like this. So this is the plane 4, minus 2, 1. Well, I can just write it this way. This is actually this is what the plane would look like if we're trying to draw this orthogonal. I mean, geometrically.
Sure. Visually, I'm thinking like, if an arrow were coming out of that paper, or a pencil, if you were to pierce it through, it's the paper that, that forms that plane.
Yeah, sure. Okay. All right, now, we have to deal with the 1, or the minus 1. So that's a question. So let's consider two different vectors. So now we consider this one. What we really want, which is 4x minus 2y plus z, is equal to minus 1. And let's consider, let's take two different points on this plane. Okay, so for instance, I could take x1, y1, z1, that's 1 point, and x2, y2, z2. Okay, so these 2 points are both on the plane. So that means that we can write 4x1 minus 2y1 plus z1 equals minus 1. That's true. And we also have 4x2 minus 2y2 plus z2 is equal to minus 1. Okay. All right, so what happens if we subtract these two?
Well, how I'd see it is you end up with 0 on both sides. So you'd essentially cancel both out.
Well, this has x1, x2, this one has x1, this one has x2, so there's no cancellation here.
Sure, you're right. So then it would be, you could write it as 4 open parentheses x1 minus x2 close parentheses.
Yes.
And then extend that for the y's and the z's as well.
Okay, sure. All right, now look. We have reduced this case to our original case. You see the relation?
Yes.
Okay. So what does this tell me? This tells me that x1 minus x2, y1 minus y2, z1 minus z2. What about this vector?
So that vector is what is going to be orthogonal to what we, or at a right angle to what we were looking at before.
Yes, it's perpendicular to this vector.
Sure.
Sorry, it's 4 minus 2, 1. 1. Okay? So if I take any 2 points on the plane, and I take their difference vector, it's perpendicular to this vector.
that's a clever trick because that'll work with any constant or coefficient.
Yes,
So-
that's in fact that's a general case. That's a general situation. All right. So so if I take one point on the plane, let me go ahead and let me go ahead and draw the axes again, and we'll quickly draw my point. All right. So this was 4, and then -2, and then 1. So it's up here, and I'll draw my red vector again. All right, now, so that's my red vector. Now let me take any point here. Let's do another color here. So here's my point. I don't even know where it is. It may be up here. X1, Y1, Z1. Let's suppose this point is on the plane. Okay. Actually, let me not draw it over there. Let me move it over so it actually works a little better. I'll move it up over here. Okay. Now, I want to describe where x2, y2, z2 could be. The point is that if I have x2, y2, z2, then the difference vector, so let me do x2, y2, z2 here. The difference vector here must be perpendicular to this red vector. All the difference vectors must be perpendicular to this red vector. So that means that this is actually still a plane that is perpendicular to the red vector.
If I were thinking of it visually like a sheet of paper, I'm just sliding that sheet of paper forward or backward along that vector.
Exactly.
Hit either one of those points.
That's what the -1 does. It slides it along the vector.
Interesting.
Okay, so that's the geometrical idea, that 4x plus 2y, or -2y, plus z, equals, I can just say any constant here, c, is a plane perpendicular to 4 minus 2, 1. And of course, it doesn't depend on this particular vector. I can have any vector here.
Hey, you're going to get me in trouble. I'm talking to someone. Here, come with me.
Does he want to join?
Yeah, I was about to say he was wanting some more heart cereal. My apologies.
Okay. All right. So we got this. All right. Now, remember, so far we've only been dealing with one of our two planes. Well, we have two planes. We have two planes here. This one here, I'm just going to grab this again and bring it down. We have two planes.
Apologies. Thank you.
Yeah, no problem. So let's just say this plane 1 is perpendicular to 4 minus 2, 1. Plane 2 is perpendicular to, well, what did I put here?
Oh, -2, -1, -2.
Okay. Okay, so you see that this -1 did not come into anything about the direction. -1 doesn't give any direction information.
Sure.
All right, so remember, what we want now is the cosine of the angles between the planes. So how do we do this? If I was going to do this, I was going to draw this schematically, right? Here's my vector 4 minus 2, 1, and I have a plane perpendicular to that. Then I have another vector, which I can do in another color. Let's do orange. Maybe this way. So this vector is minus, I'm not drawing the scale.
Sure.
Okay. And this vector and this plane goes in that direction. And I want the angles between these two planes. So how am I going to get that?
I would suppose it comes down to finding the angle between the two vectors themselves.
Okay. Yeah, no, but the vectors aren't in the plane.
Oh, okay, yeah. Oh, I see.
The vectors aren't in the planes.
Sure. So you could calculate a. So one option that I'm thinking of just out loud is you could calculate a normal vector off of each plane,
Right.
and then use those normal vectors, and then the formula we earlier were playing with, dealing with the dot product being equal to the magnitude of each of the vectors times cosine of theta.
All right. Now there's a problem with that. If you look at this geometry, look at this vector here, and look at this plane. How would I draw a normal vector to this?
I would have to come up with a vector
Okay.
that passes along in the plane.
All right. Yes, I could take a vector in the plane, like that one,
Sure.
right? But I could also take this one, or I could also take this one, or this one. Which one am I going to take?
Gotcha.
So that's a problem.
Sure. So then, next idea, and out of curiosity, can we just work with the current vectors that we have or that we are using for our planes?
All right.
So,
Well, does that make sense geometrically? I mean, if you put your fingers up there, if you take the angle between these vectors, the plane, they're basically showing you which direction the plane is going. So it is true. In fact, the directions of the perpendiculars determine the directions of the plane.
Okay. Interesting.
Right? I mean, the perpendicular is showing you which direction the plane is facing.
That's a good point.
So if you take those two directions, that's going to show the angle between the facing directions. So that is, in fact, the angle that you want.
Excellent.
All right. So let's finish this up then.
Good. Okay.
I'll bring down this formula, and let's just make sure that you've got this one down. Okay, so what do I do?
All right. So start with the dot product.
Okay.
I figure we would look at is the two vectors that we have.
Right.
Of course, calculate the dot product, which, if I can recall, is multiplying each of the terms in pairs. So
Okay.
it would be 4 times -2, -2 times 1, 1 times -3, and adding those subsequent pairs together.
Okay, so what do we get here? -8, -2, is that -10, is that -13?
That's how yep.
Okay. Okay. All right, so that's my dot product. Okay, now what do I do?
So now it's going to be the extended version of the Pythagorean theorem for each
Okay.
of the vectors.
All right. So what do I write?
So let's see. So square root of 4 squared plus -2 in parentheses squared plus 1 squared. And of course, all underneath that radical.
Right.
So come out to what? Square root of 21?
I guess so, yeah.
And then the similar operation for b. Square root of -2 squared in parentheses, of course. 1
Okay.
squared, -3 squared in
Okay.
parentheses.
Okay.
So let's see.
Okay, let's see.
14, perhaps?
I think so, yeah. Okay. And this was U, and this was V.
Mhm. Yes, sir.
All right. So, all right. So now what do I do?
All right, so we've got a beautiful operation here. So how I see it, just to make things nice and easy, is divide, we can combine the radicals, and so have one large radical, 21 times 14.
Okay.
But that'll be all underneath -15, so we can divide that over to the left and get prepared to
Okay.
work with arc cosine or cosine inverse.
Okay. All right. So you're dividing to the left. So what you want to do is take this and get. You want to get a formula for cosine.
Yes, sir.
So that's. All right, so you're saying here's my denominator, here's my numerator. So we have minus 13 over square root of 21 times. Can we simplify this at all?
The 21 times 14, I probably, let's see, 210 plus 84, 294?
Okay.
Might be taking the easy approach on that one. I apologize.
I think there's an easier way, yeah.
Okay, let's see. Perfect. Oh, wait a minute. Okay, you could pull out a 7.
Right.
The 7 root 6.
Okay. And of course, you can put the 6 on top, and you can take what they call rationalizing, right? You can multiply top and bottom by square root of 6.
Yes.
And then this would be 42. And this does look like it's less than 1, which it should be. So I think we're in good shape.
Excellent.
All right, good. I mean, I like to do these out so that you can see, because all of these problems do have a geometrical interpretation, and I think it's quite important to understand the geometry, because otherwise you get lost. So let's see if we can knock off one more problem here. We got about 13 minutes.
Cool.
Let's see what we have here. All right, how about this one? Number 8. Let's see what we can do with that.
Sure.
I'll move down here. There we go. All right. Oh, sorry, that's not. Didn't mean to do that. Okay. All right. So what are we going to do here? Well, let's do some visualization. It's always good to visualize. So let's go ahead and draw what we got. So you got 3 points. Because another good thing for drawing what you got is you can tell whether your answer makes sense. So let's see. If I do x, y, z like this, and then I get minus 1, and then 2, and then 4, minus 4. Oh, it's going to be down here. So that's minus 1, 2, minus 4. And then here I have minus 2, minus 1, minus 2. Too many minuses here. Minus 2, minus 1, minus 2. So that's going to be somewhere down here. So that's going to be minus 2, minus 1, minus 2. And then this one, minus 2, 0, 0. That's over here. So it's a little hard to see where it's going to be. But you know that 3 points determine a plane, so there should be a unique plane that contains all these 3.
Sure.
So how to find it is the question.
Perfect.
So any ideas?
Well, that's where I'm trying to put it together. So, trying to think about what I know of putting together planes. I mean, of course, some options might be creating vectors based on each of those coordinates.
Okay.
That's one thing that comes to mind as just something to play with.
All right, that's something that you could do. So you have 3 vectors like this. But of course, those vectors are not actually in the plane.
Mm-hmm. Just their endpoints.
Just their endpoints.
Could there be something to say for maybe finding the magnitude of each of those vectors?
All right, you could find the magnitude, but that's kind of hard to see how those would combine to get you a plane. I mean, you've got your 3 fingers going out like this, and the 3 tips of your fingers are on the plane, but that doesn't really tell you anything about the plane itself.
So what would be a good first step then?
All right, well then let's all right, so now the advantage of linear algebra is you can think about it geometrically and algebraically. We know that the equation of a plane has the form what does the equation of a plane look like?
I would assume, based on recollection, that it would be some form of a times x plus b times y plus c times z.
Yes.
D for some a, b, c, and
All right.
D.
Exactly. Okay. So we need to find A, B, C, and D. So can we use this information to find A, B, C, and D? Now, it told you something also. I told you in the problem this.
The coefficient is negative 8.
Okay, so that gives us, what does that tell us?
Ah, okay. So that tells us A.
Okay. Why did it disappear? Okay. Was it 8 or negative 8? I think it was. Here, let me,
Oh, goodness. I believe it said negative 8.
okay, let's see. Yeah, negative 8, yes, okay. All right, so I think we've gone as far as geometry is going to take us. Well, one thing is that now we want the geometrical what's the geometrical significance of these three vectors now?
Sure. So, well, you know that that first vector of negative 2, 0, 0
Yeah.
seems rather interesting.
Yeah.
That we could work with the negative 8 and work backwards from that.
Okay. Sure. All right, so let's look at negative 2, 0, 0. What does that tell us?
Let's see. Negative 2x plus 0y plus 0z.
Well, wait a minute. These aren't A, B, and C.
Oh, yeah. Sorry about that.
This is a point in the plane.
So, I wonder, could those be solutions?
Yeah. Yes, that's the key observation here. This is a solution. It's a solution.
But then I wonder, could we create a system of equations then with the solutions being each of those items?
Yes.
Okay. And then A, of course, would be the negative 8 that we've carried.
Okay. All right, so tell me what's my system of equations that I need? What's the first equation in my system?
Okay, so we're probably going to run with negative 8x plus by plus cz
Okay.
equals, and this is where I'm going to take a guess and say negative 2.
All right, now, you said that this is a solution. All right. Now think about, here, let's just give some simple example. 5x equals 10. What's the solution to this?
2.
2. Where do you put the solution? Where does the solution belong in the equation?
Got it. Okay. And so at the end, what we could do is maybe qualify it as 16.
Well, or for instance, if I have something like this, 3x minus 7y is equal to minus 4. A solution to this would be 1, 1, right?
Mm-hmm.
Where do you put the 1, 1?
Into each of the coordinates.
Into the coordinate, into the x and the y.
Oh, okay. So then if we were to plug in those values, it should come out, instead of negative 2, come out to positive 16?
All right, so this is not correct. You do have to plug in these values. We started out with this, right?
Mm-hmm.
So what you want to do is plug this in. You want x, y, z is this. You plug your values into the variables.
Perfect. That makes sense.
because this is a solution. So you get, like you said, you get negative 8 times minus 2 plus, and then these just zero out.
Mm-hmm.
So we get, and so here we get minus 16. So what does that tell me?
And so, working backwards. Now, is it negative 16 or positive 16?
It's a positive 16. Yeah, sorry.
Okay, no worries. Okay, so that tells us I wonder if we could use that with another one of the points to work back. Well, I don't know.
Well, all right. Let me go backwards a little bit.
Mm-hmm.
Actually, let's just do this. What am I doing here? I'm plugging these values, minus 2, 0, 0, in for x, y, and z. Let me just do that. Okay, so I have minus 8 times minus 2, plus b times 0, plus c times 0, equals d.
So could we repeat this algorithm for each of the points?
Sure. So let's do that. Let's do the second one. The next one, so there are three of them. Let's see, what was the next one? We had minus 2, minus 1, minus 2. So that tells me that negative 8 times minus 2 plus b times minus 1 plus c times minus 2 is also equal to d. And then my last one was minus 1, 2, minus 4. So that's going to be negative 8 times minus 1 plus b times 2 plus c times minus 4 is equal to d. So where do I go from here?
So now, will the d be constant between all three of those systems? Is that the idea if we're trying to come up with the singular equation that represents this plane?
Well, we are trying to find b, c, and d.
Okay, so then we can make the claim that d should be 16.
Okay, all right, so the first equation gives me d equals 16. Okay, then what can I do?
So immediately, substituting that in for everything else,
Okay,
that would allow us to take this function into a 2-by-2 system of equations.
okay, yes. So the key thing now is that b and c, these are my variables. Those are what I'm solving for. Okay, here, so from this point you just solve for b and c.
Perfect.
All right. And you can see that, in fact, this is a general procedure that you could always do. If I gave you any 3 points, you should be able to use this procedure to find a plane. If I gave you 5 points in 5-dimensional space, you should be able to find a 5-dimensional plane that contains those 5 points. I can give you a 5,000-dimensional, 5,000 points in 5,000-dimensional space. And that's no joke. There are applications where you want to do that.
That's really cool. And out of curiosity, so we were lucky in the fact that we had you given to us so early. If we hadn't, then it would just have been a matter of utilizing, the properties of linear algebra. Solving using maybe reduced row echelon form.
Yes.
Or elimination.
Yes. What you want to do, basically, the trick to linear algebra is turn everything into a matrix equation. Once you have a matrix equation, then you assume that you have a solver somewhere that can solve it. Once you've gotten that far, you're done with the problem. So that should kind of be your goal. How can I relate this to a matrix equation?
Perfect. That's awesome. Well, thank you so much.
Okay. All right, good. Well, that's been about 40 minutes, and I think Zoom will give me a hard stop. Well, actually, I think that Zoom has decided to give me unlimited time. But anyway, I try to keep this to 40 minutes. So,
I appreciate that, sir. Thank you again